Welcome to this video on JVM Architecture. Today, we'll explore the internal components that enable Java applications to run efficiently. When you execute a Java program, the JVM does much more than just run code. It manages memory, handles threads, and performs garbage collection. Understanding these processes is crucial for optimizing performance and mastering advanced Java concepts. In this video, we'll dive into the Class Loader Subsystem, Runtime Data Areas, heap and stack memory, the method area, the program counter, and the vital role of garbage collection. We will also examine the just-in-time compiler to see how bytecode is optimized into native machine code. By the end, you'll be well prepared to explain JVM internals and interviews and build better applications. Let's begin with the Class Loader Subsystem. Before execution, every Java class must be loaded into memory. This process involves three main phases: loading, which creates class objects, linking, and initialization. The linking phase includes verification, preparation, and resolution. Following this, the initialization phase handles static variables and blocks. Java uses different class loaders, such as the Bootstrap class loader for core classes and the Platform class loader for libraries. The Application class loader loads user-defined classes. These loaders follow a parent delegation model, which helps ensure security and prevents the duplicate loading of classes. Next are the Runtime Data Areas. These are memory regions allocated by the JVM. They're split into shared memory, accessible by all threads, including the heap and method area, and thread-specific memory, containing the stack, PC register, and native method stack. Heap memory is the largest area in the JVM. It is used to store objects and instance variables. For example, when you instantiate a class, that object resides in the heap. The heap is structured into generations, starting with the young generation for new objects. The young generation includes Eden and survivor spaces, while the old generation stores long-lived objects. A common interview question is what causes an out-of-memory error, which occurs when the JVM can no longer allocate additional heap space. Stack memory is thread-specific. It is used for method calls, local variables, and object references. If you declare a local primitive variable within a method, that variable is stored directly on the stack. Every method call creates a stack frame containing local variables, the operand stack, and the return address. Once a method completes, its frame is removed. Excessive recursion can lead to a stack overflow error due to stack exhaustion. The method area is a shared memory region that stores class-level information. This includes class metadata, static variables, method details, and the runtime constant pool. It is accessible to all threads. The program counter register is unique to each thread. It tracks the currently executing instruction, acting like a bookmark to help the JVM resume correctly after a context switch. Finally, the execution engine runs the bytecode. Its core components are the interpreter, the JT compiler for performance optimization, and the garbage collector, which manages memory automatically. The interpreter reads bytecode instructions one by one. While it is simple and starts up quickly, it can be slower for repeated code. This limitation led to the development of the JIT compiler. JIT stands for Just-in-Time Compiler. Its purpose is to improve performance by converting frequently executed bytecode into native machine code, significantly reducing interpretation overhead and ensuring modern Java applications run efficiently. Garbage collection is a major Java advantage, as it automatically manages memory by removing unused objects. It works by identifying reachable objects, locating unreachable ones, and then reclaiming the memory they occupied. Garbage collection types include minor GC for the young generation, major GC for the old generation, and full GC, which cleans the entire heap. These processes prevent memory leaks and improve overall system reliability. The Native Method Interface, or JNI, allows Java to communicate with platform-specific code, such as C or C++ libraries. This is essential for system-level integrations, like those used in the Android framework. Mastering these concepts prepares you well for technical interviews. Common questions include differences between heap and stack, how class loading works, and the causes of memory-related errors like out-of-memory error. In this video, we have covered the key pillars of JVM architecture, including the Class Loader Subsystem, memory regions, the execution engine, and garbage collection. These are fundamental for any Java developer. Understanding these internals is essential for optimizing your applications at runtime. In our next video, we will dive deeper into the Class Loader Subsystem and explore how Java classes are loaded into memory step by step.